So our next stop in the land of invariance for knots is going to be to study whether or not we can color a knot diagram in a particular way. Colorability for knots. And why I like this is it's a simple idea to grasp what actually goes on with knot colorings. But of course, like with a lot of things in math, it's very challenging to know the whole story, right? And there's a lot of really interesting theory behind it. But the basic idea behind colorability for a knot is we take a knot diagram, like one of the diagrams that's up here, and we make an effort to assign to every arc in this diagram a color. So, for example, when I say arc, I mean an unbroken strand inside of our diagram. So, for example, this purple piece right there would be one arc in this diagram for 7-1. Right? And so the diagram for 7-1 over here on the left side actually has 7 arcs in it. So there's the second one, there's the third one, there's the fourth one. And notice that as I'm coloring these, I'm trying to use a different color for each one. And that's something we can always do, right? However many arcs we have in a diagram, we can always assign each one of them a different color. And that gives me some scheme for coloring this. So this is arc number 6, and then here comes arc number 7. Oh, what color do I even have left? White. Yeah, let's just leave it as white. Sort of whiten it up a little bit. So there's an example of 1, 2, 3, 4, 5, 6, 7 coloring. So we're going to call that a 7 coloration of this knot. And so we'll say that this knot is 7 colorable, right? Because there's a way of assigning 7 different colors to its 7 different colors to its arcs, with the requirement. So anytime we create a coloration of an arc, or of a knot rather, that we're going to require that at a crossing, one or the other of these things is true. Either all colors are different at a given crossing, and that's borne out by this, right? If we pick any one of these crossings, at each crossing, we kind of think of there as being 3 arcs that are incident on that crossing. There's the one that's the overstrand, yellow in this case, and then there's the 2 pieces of arc which make up the understrand, right? And here, those 2 have different colors, right? So green here, blue there, and yellow there. So at this crossing, all the incident arcs have different colors, and that's true of all 7 crossings in this coloration of 7-1. The other possibility for a coloration is that all the colors are the same at a given crossing. So, for example, it would also be valid to take a knot diagram, like the one I have over here on the right for 6-2, and just color all of its arcs the same color. That's what we might call a trivial coloration.
So you could do either?
We could do either. Or we could do some combination. Right? There may be a way of assigning colors to the arcs where some of the crossings have all colors the same and other crossings have all colors different. And that would still be a valid coloration. Right? So here's a 1 coloration of the knot 6-2. So every knot is 1 colorable because of that allowance here for all the colors to be the same at every crossing. So it's not very interesting for a knot that has n arcs in it. It's not very interesting to ask whether it's n colorable, because you can always just assign every arc a different color, and therefore the all colors different will be satisfied. And it's also not very interesting to ask which knots are 1 colorable, because we can always just color the whole diagram the same color, and all the colors are going to be the same at every crossing. So of course the interesting question is in the middle. Is there a way for me to color a knot diagram with n crossings using more than 1 but fewer than n colors? Right? And if we can find 2 knots, one of which is 4 colorable, let's say, but the other one is not 4 colorable, is that going to be enough for us to conclude that those 2 must be different knots? Because 2 knots which are the same knot, we should be able to rearrange their knot diagrams in a way such that we can apply the same coloring scheme to each one of them. Right. So if one of them is n colorable, the other one's also n colorable. If one of them is not, then the other one is not. Right? So somehow, broadly speaking, we want for the colorability properties of a knot to be a complete invariant for that knot. Ideally, if we can know everything about how a knot may be colored, that should uniquely characterize the knot for us. So that's our holy grail this semester, is a complete invariant for knots, the way that we had a complete invariant for rational tangles, right? And colorability is going to be the way that we get there. But the algebra gets really interesting now when we start to push that envelope. Because how do we actually encode colorability information for knots inside of an algebraic structure? That's going to be that's going to be where we stretch ourselves to as we go forward. So that's the broad question about colorability.